So we're going to talk a little bit about some work that John, Bob, Ray, and I have been thinking about. This is more of a concept presentation rather than we've necessarily made any fundamental work here. So this is more thinking about that hypothetical of how would you integrate machine learning models into Soar, something that John alluded to in his Soar introduction at the beginning of the workshop. So let's get into it. You may have heard about Transformers. They've gotten some popular press in the last couple of years. The kind of the most famous one was put out with OpenAI. You may have seen it in the press as a fake news generator or a fake text generator. They also were some ethical implications around its release because human users found it difficult to disambiguate between machine generated text and text actually generated by people. So there was some consternation about the ethics of actually releasing it. But it was released. And if you're not familiar with GPT-2 or transformer models, here's really a good way to think about them. They really just complete text. So here I'll type in some generic text associated with John Laird here. And what you see with the text completion is it's really, really good about picking up in subtleties about the text. So if I just type in cognitive architectures in a citation, there's really nothing about this text besides the citation that suggests that it's academic text. But the GPT-2 model here, it's been pre-trained on some journal articles, is actually able to complete, this citation heavy corresponding text with really just one cue, which is pretty cool. And in general, you can see here that it's learned a lot about some of the style, the syntax of academic writing in general. So GPT-2 and this kind of transformer family of models has really become, I would say, the forefront of natural language processing research. So they do have state-of-the-art or close to state-of-the-art results across a variety of benchmarks. One of the interesting things about transformers is these state-of-the-art results have come at a cost. They have a ton of parameters associated with them. So you might think that a machine learning model, if it has a lot of parameters, might have 10 million parameters or 100 million parameters. Here, there's been a huge explosion. GPT-2, the largest version of GPT-2, had 1.5 billion parameters. That was released in February of 2019. And you can see here, Microsoft has released a Turing NLG model that has 17 billion parameters. And actually, over the weekend, OpenAI announced GPT-3, which has 10 times as many parameters, about 175 billion parameters. So really an explosion in parameters. And there's some trade-offs associated with that parameter explosion. So I'll get into some more specifics about how we're thinking about transformers. Specifically, transformers take in a large amount of pre-trained text. And so there's a pre-training process that takes in unconstrained general text, maybe general text from the internet, maybe Wikipedia, and it learns a prediction task. So it's unsupervised. There's that base level unsupervised task of, well, it's a good language model if it can predict language that's close to what's in this text corpus that I've assembled. And similarly, you can think of language models as being either general or domain specific. So this is a good way to make a general purpose language model. Is give it a bunch of text. Can it predict the text in that corpus? Then great, you have a general purpose language model. But given the source of this text is really just internet web pages, you kind of think about also corresponding problems related to domain specific text. So you're thinking of text that is maybe coming out of specialized scientific material, maybe specialized military material, such as a training manual or a tactical manual. And those types of resources will have terminology, jargon, syntax that's specialized, that is unlikely to be reflected in, for example, general English, or if it is reflected in your general English corpus, it is probably not reflected to the same probability distribution, right? Those jargon words will not be showing up in the same way or very commonly, or or at all, right? So there's a frequency mismatch between these specialized text corpora that you might find in an application domain versus general purpose English. And there's a fine tuning process that basically applies the same thing. So instead of training the model from scratch, you're starting with the same model weights from the pre-trained model, and you're really just updating them to get your language model in compliance with the statistical realities of that specialized domain. And a further process you can think of is, and this is more of the concept of how do you expose knowledge in a transformer model. So a transformer model has learned these really rich relationships, and we know that those relationships exist in the transformer model because it can produce text, right? So, and the text exposes some of those relationships, but you don't necessarily want to do natural language processing with Soar in order to get that information extracted from the transformer model. So instead, the technique that we've been applying is fine tuning based on a structured task. So you could think of maybe an example task being a hypernym type task where you've got X is a Y, or a dog is a mammal, is an organism, right? There's a hierarchy associated with that. So what we can do is we can supply some example structured task data, fine tune it, and now we've got an interface or a lens into the knowledge that's been learned by transformer models. So if it's learned a terminology, kind of the hypothesis here, if it's learned some terminology upstream, then when we get to these downstream specific structured task domains, we're able to go ahead and grab that knowledge, even if in that specific structured task data, we did not train on that specific knowledge. So it's kind of a transfer effect where knowledge that was learned from general text corpus is exposed in these very like specific task oriented domains. So just to give another example about how a transformer model can be applied. Here's kind of an X-ray into a transformer model that we've applied in a WordNet domain related to hypo and hypernyms. So here, there's kind of a frequency effect with transformers. So if you were to say to a transformer model, hey, define the word infernal, infernal is, at least in my mind, more frequently associated with maybe hellfire or fire in general, something associated with heat, right? A furnace, maybe it would be the root word for that. And in this case, we'd actually like to get it in a different domain. So in this case, we have a zombie type domain, right? We have the undead awakening from an awakening from a roar in this context. And what we're actually able to do is condition the the transformer model in order to get at this context. So what we do is we supply some context for the word sense, and the output here, and again, we're in a hypernym domain. So an infernal is a dead person, is a person, is a causal agent, right? So we're able to see the conditioning effect in this example. And actually, cognitive architectures and these more data-driven approaches are surprisingly complementary. So cognitive architectures, at least in my experience as an agent developer, uh, work well when you're doing like a simple example, but quickly when you deal with the kind of the complex reality of a lot of application domains, quickly fail to scale in a cost-effective way. So you need to produce a lot of engineered knowledge in a new domain, and that just takes a ton of time. Whereas with a data-driven approach, and especially when you're working in unsupervised learning, the scalability properties are just fantastic, right? You give it a big pile of data and it has learned something about that data, and then you can transfer that learning into the application domain you actually care about. But as a result of that kind of initial pre-training process, you're not really quite sure what you've learned. You could have learned anything. You didn't take a careful look at that underlying data. So there is an unpredictable effect where you're not really quite sure what you learned. Does it match your operational environment? Maybe, maybe not. It's hard to verify. So there's kind of this unpredictable nature of data-driven approaches. Whereas with cognitive architectures, right, there's a lot of certainty about your result. You're going to get a lot of repeatability, a lot of predictability associated with any approach that's rooted in a cognitive architecture. So what we'd like to do is try to see if we can get a best of both worlds approach where we can reliably adapt cognitive architectures to new unseen tasks on the fly. So can we take advantage of all this natural language processing goodness associated with transformers and all the knowledge it's learned to compute knowledge on the fly without having to recode or retrain our agent? And this is one of the architectural variations that we've been considering, what John alluded to in his introduction, which is taking a task specific transformer model and integrating it with potentially semantic memory, having a query response mechanism. So you can imagine this existing alongside semantic memory or maybe being integrated inside semantic memory so that you can, for example, expand your declarative knowledge base. So you've got some related knowledge that has ended up in semantic memory and you like to expand it with a transformer model. Similarly, you can also imagine querying the transformer model in real time based on your domain. So perhaps if you've encountered some facts about an object, but if you're not quite sure what the name is, that could be one way to query your transformer model. You could have a transformer model associated with maybe a reverse dictionary. So given some attributes associated with something, can I classify it as a stop sign, for example? And this would allow you to generalize, right, and kind of understand that I'm seeing certain properties about the world, and do I understand what that is? Well, my transformer model says that if it's red and it has a particular shape within this particular geography or political region, then that must mean it's a stop sign here, even though in my computer vision model or in my semantic memory, I don't have that exact fact. You're able to compute that necessary information on the fly. Other opportunities for integration include really this unpredictable nature of transformers. So a transformer model hypothetically could tell you anything because the underlying training data was unconstrained. And it's actually even a challenge we have after several layers of fine tuning. Oftentimes, the transformer model will still try to, for example, predict a sentence when we've tried to train it out of that behavior. So it is kind of a challenge applying these approaches. And an agent, in contrast, actually has quite a bit of consistent semantic knowledge about the world. So that can be an opportunity for some consistency checks, right? So transformer model told us something about the world. Well, maybe we can fact check that with our semantic memory and decide if that is actually something we'd like to take as fact or reject it because it's inconsistent with what we know is true about reality. And that agent context could also be applied as a conditioning statement that would allow transformer models to understand the specific context in which it's generating knowledge. So going back to that WordNet example, right? Thinking of ephemeral and the various word senses of that word, if you can supply context to narrow down that specific word sense you're interested in, then you get a more accurate result that way. So going through nuggets and coal, some nuggets associated with transformer integration, I think would be definitely lower LOE for building agents, especially if you're wanting to create general agents that will specifically adapt to certain task environments. I think this is a great opportunity to apply transformers in those kind of specification domains or specialization domains. Uh, Transformer models, you can kind of think of them as maybe a world model. So a really rich knowledge source that if you can figure out how to query it, you can certainly query it and understand at kind of an encyclopedic level what's going on with what you're seeing on your input link, for example. And there's a lot of consternation around trust properties related with transformer models since it's really been trained on unspecified, just general purpose text. There's a lot of, I would say, fear that there might be some statistical properties that are just completely unrealistic. Maybe it's learned something that's false, right? or it's biased in some way given the specific maybe web sources that it was used to train it, and checking the consistency between a transformer model and a cognitive architecture can be a great way of improving the trust in that transformer model. Cole, Transformers introduce quite a bit of complexity. So if you can imagine, these are massive, large parameter models. So you need at least one GPU, if not several GPUs, depending on the specific transformer model that you're looking into. And that induces some latency, right? You're having to copy this model into VRAM on your GPU, query it, and get a response. So that creates some increased hardware requirements. And if you wanted to use this in a real-time system within Soar, you would almost certainly have to have at least one GPU running on the machine where the Soar kernel is. So that's a fairly large hardware constraint. Also, if you wanted to pre-compute fine-tune models, that seems fine. But if you're wanting to do this on the fly within the agent, there's quite a bit of latency involved in the fine-tuning process. So there may be some improvement with GPT-3, which is fairly new. The pre-trained models for that haven't been released, but there's some evidence in the initial GPT-3 paper out of OpenAI that it has much better performance in zero-shot or few-shot task cases.